All right, welcome to this video. Now, in this video, we're gonna study the module called the Chemical Engineering Thermodynamics 2. And the first unit that we're gonna look at, which is unit number 1, it's called the volumetric properties of pure fluids. Now, starting with this unit, it is really not far-fetched from what we did in Chemical Engineering Thermodynamics 1. So here we're going to do Thermodynamics 2, which is more or less as the continuation of what we did, but now most definitely we're gonna learn more new concepts or more new units, right? So without wasting any time, let us just go through the content and try to analyze this content. But firstly, we're gonna look at the outcomes of this content, of this unit. Now, looking at the outcomes, what are we actually looking at? We're gonna start with outcome number 1. We're actually gonna learn on how to determine the state or phase of a given fluid at given conditions, right? So it's very important to know the state of a given fluid. Remember, a fluid, we can talk about the gas or a vapor. We can talk about the liquid, right? So at the same time, we need to know how to determine the state or the phase of that fluid, whether the fluid, it is in liquid, or the fluid, it is in gas, or the fluid, it is in solid. That's the first outcome. And then the second outcome, which is this one over here, we're gonna learn on how to define a pure substance. You did this in high school. You've learned on how to define the pure substance. So most of the times, we need to know the difference between the pure substances and the mixtures, right? We need to be able to distinguish when we talk about the pure substances and the mixtures. So we're gonna look at the mixtures as well as the pure substances. And then the other outcome that we're gonna have to focus on to, we're gonna have to learn, we're gonna have to understand and be able to describe what we call the PVT, whereby P simply means the pressure, V volume, T means the temperature. So we're gonna have to understand and describe the PVT behavior of pure substances. That is, we're gonna look at the PV diagram, we're gonna look at the PT diagram, and we're also gonna look at the TV diagrams, or we can call them the property diagrams. Why do we call them the property diagrams? Because there are three properties that we are actually looking at. We are looking at property pressure, volume, as well as the temperature, right? And we need to be able to distinguish what type of properties are we actually looking at. Is it intensive properties, or are we talking about the extensive properties? We need to know the difference and different types of examples of those, right? So that we can understand, based on these outcomes, what are we actually talking about. And also, we're going to talk about the PVT surfaces of pure substances. And therefore, another outcome, we're gonna learn and be able to understand the different types of equations of states, right? So the equation of state, we spoke about this, right? When you spoke about the ideal gas equation of state, right? The Van der Waals equations. So those equations are the equation of states, right? Because remember, when you talk about the states, we are referring to the phases, but we'll do that again when we get there. And therefore, another outcome, we're gonna look at we're gonna calculate the volumetric properties using the equations of state and generalize the correlation for a given system. So basically, from this learning outcome coming to here, it is just an integration. We integrate this learning outcome to this one. But what we know is we're going to have to look at the correlation. When we talk about the correlation, we are talking about the relationships, right? Remember, we are talking about the properties. So there must be generalized relationship for a given system. We have two systems, and then we're going to look at the relationship between those two systems using the calculated parameters from the equations of state. And therefore, another outcome that we're going to look at, we're going to have to identify the applicability and limitation of every equation of state, right? It is self-explanatory. Just identify, right? And limitations. And then the last one, we're going to learn to determine the volumetric properties from the thermodynamic tables and diagrams, which I all believe this outcome we are familiar with from thermodynamics 1, right? So these are basically our outcomes. So now, why do we study this unit? Why should we study the volumetric properties of fluids? Now, I'll tell you this, right? Um, Basically, we study this to talk about the energy and to talk about the work of a chemical engineering thermodynamic process that we see over here. These are just only two processes that I actually wanted to focus on too. Having a look at this schematic diagram over here, we have the process which is called a steam power plant. Now, what is the objective of a steam power plant? It is basically to use water as a work substance. So in this case, because we want to use water, we're going to heat up water during the whole process so that we can form steam, which is simple steam power plant. So the steam can be used to generate electricity as we see over here. So the whole, this is the chemical engineering process, chemical engineering thermodynamic process, what we see over here. So what we're gonna do is we're gonna we should be able to know how to determine the work. We should be able to know how to determine the energy using the enthalpies and the internal energy of this system. You understand what I'm saying? But in order for us to determine the work, the energy of the system, we're going to use the data of enthalpies and we're going to use the data of the internal energies. But the question is, how are we going to get those internal energies and enthalpies? We're going to use those properties that we have just mentioned, right? We're going to measure those properties that we have just mentioned. You will see how by saying this, which I believe we are quite familiar with this because we would use the specific volumes, would use the pressures, would use the temperatures to read from the steam tables, and then we calculate all of those energies, we calculate all of those works. Basically, that's what is basically happening in a nutshell in this concept over here, in this unit over here. And therefore, again, having a look at this schematic diagram, we have a simple refrigeration cycle, right? So now in this case, what do we do here? We need what? We need substance to boil, right? From liquid to vapor. Remember, I said we're going to look at the phase changes. So the objective of this refrigeration cycle, it is to do what? It is to boil from liquid. We are boiling liquid to vapor. That's what we are doing. And therefore, after boiling that at low temperatures, then this process of boiling liquid to vapor will then absorb the energy, right? Will then absorb the energy from the cold space, keeping it cold. And therefore now we have the refrigeration where we know how does the refrigerator actually works. It keeps our food or our whatever in the refrigerator cold or cool. You understand what I'm saying? So basically, we are using those properties to get the energies, right? And I believe this schematic diagram over here, we are all familiar with this from thermodynamics 1. So now, what we're going to start looking at based off the outcomes and the purpose of us learning this module over here, this unit over here, we firstly gonna look at the definitions and explain those definitions before we get before we complicate ourselves throughout the entire unit. So let's break out the definitions, we understand them. Therefore, when we go through the unit now, we will be able to understand what is the unit all about. Now, firstly, we're going to look at these definitions. When you start thermodynamics, these are the basic definitions that you need to understand, right? The system, we are all familiar with the system, the term system, right? So when you talk about the system, we are talking about a body of matter with finite boundaries, whether it could be physical or it could be virtual, right? So for an example, I'll draw a sec. Okay, by the way, I have the squares over here. These squares, they indicate the system. And then the white background where these squares are placed, it will represent the environment. So you see, in this blue squares, there is something that is happening there. So whatever that is happening inside of these boundaries, we see we have the boundaries over here. Whatever that is happening inside of these boundaries, it is actually separated from the environment. The environment, it is the white background that we see over there. So for a fact that it is whatever that is happening here, it is separated from the environment. That means this is what we call the system. Okay. So there are two types of systems. In fact, there are three of them. We have the isolated system, but I just want to focus only on these two types of system, where we have the open system and then we have the closed system. So the picture over here, it simply explains what does an open system actually talks about. Here we are talking about the loss of heat to the environment. We are also losing the matter to the environment. For an example, we know that there could be a phase change during the whole process of the system. For an example, a liquid can change into vapor, but because the system it is open, therefore the vapor will escape out of the system. Because the system it is open, it doesn't have a lid. So that means the matter will escape, matter referring to the mass, right? Or whatever. So matter will escape out of the system. And then here, having a look at this box over here, we can see that we have a lid with a black color. So in this case, the only thing that can escape out of this system, it is heat. Remember, heat, it is also regarded as energy. So that means this system can give energy to the surroundings or to the environment. But because it is closed, even if there are reactions that are taking place inside of this system, and then the byproducts of those reactions, it turns out to be the gases. So those the gas molecules won't be able to escape, will be trapped inside of the system because the system, it is closed. Simple as that. So it's important to understand what is a system and what are two types of the systems. So the chemical engineering, thermodynamics, it focuses on the system. We look inside of the system. We're talking about the energies inside of the system. We look at the properties inside of the system. So it's very important to know what is the system. Now, as much as we looked the chemical engineering thermodynamics in a larger scale, which is we looked at it in a form of a system, you have to understand that what's happening inside of the system, we have the substances, right? And these substances, they can vary, right? And they can exist in different phases. So we need to learn, or we need to understand, when we talk about the phase, what are we talking about? It's simple, right? It's very, very simple. And this is the definition of a phase. In simple terms, how do we look at the phase? We are looking at the liquid, we are looking at the gas, we are looking at the solid, right? There are three types of phases. So when you think of a phase, think of a substance that is what? That is homogeneous, that has homogeneous intensive properties, and it is bounded by a physical surface. That physical surface will determine whether the substance, it is in liquid phase, or it is in gaseous phase, or it is in solid phase, right? It is just a simple basic definition when we talk about the phase. So having a look at this tank, we can see that we have two different substances so that exist in different phases. So for an example, I'll assume that the substance that I see at the top here, which is on phase number one, is a gas, right? Let's assume that this tank, it is closed. So here in phase one, we have a gas, which is separated from phase two. In phase two, probably maybe we have the liquid, right? We have the gaseous molecules that are just invisible at this point in time based off an assumption. So we have the gaseous molecule, and then we have the liquid molecules this side. So in the middle, we have separator, right? We have separation between the phase 1 and phase 2. We're going to call that the interface, right? So we call it the interfacial layer. So when we define the interface, it's simple, just like how we see on this diagram over here. It separates two or more phases. So these phases are solid, liquids, or we are talking about the gases. It's a simple, basic, right? So you learning all of these things, you understand them, right? But do not forget, we're going to apply all of this inside of the system, where we're going to look about the phases of our substances and the importance of their phases and how they behave, and also their properties such as pressure, temperature, and volume. Okay, it's very important. So while we are still learning the definitions and explaining them, we have what you call the thermodynamic property, right? We're talking about the properties. There are two types of properties. So here we have property A, and then here I'll call it property B, right? So now these properties are what we are quite familiar with. But the most properties that we're going to focus on too, it's pressure, temperature, and the volume. You understand, which is on this side. But you need to understand that these properties are subdivided into two. We have the intensive property. So the intensive property, it's simple. Look, intensive, independent. You understand? I. So extensive, that means it will be the dependent, right? Depends or dependent, whatever the case it could be, so that you don't mix them up. So when we talk about the intensive property, what type of properties are we talking about? We are talking about the independent of mass of the system, right? When we have a system, when you have a chemical engineering process system, we have the properties inside of that system. But those properties, we say they are independent of mass of the system. For an example, let's talk about the temperature. Just want to make sense out of this, okay? So if you have a liquid, this side and this side, say here you have less liquid, and then in this side you have more liquid. Or we can say that these two liquids, they can have the same temperature, but the substances, the level or the matter inside of this beaker and the matter inside of this beaker, it is not the same. We have more liquid this side, we have less liquid this side, but the temperatures are the same. So we can tell that the temperature, it is intensive. Why? Because it is independent of mass of the system. It does not matter how much you have this side and this side. It really does not matter, but the temperature can be the same. So the temperature, it is not affected by the matter of our by the matter inside of that system. You understand? So I'm choosing temperature because it will make sense in this case. You understand? They all make sense, but yeah. So pressure, it is also regarded to be one of the intensive property, right? It does not depend on the mass of the system. And all of these examples here, these are all examples of the intensive properties. You can go through them. And therefore now the intensive property here, we say they depend on the mass of the system, which is mass, number one, right? So for an example, this looks less, this looks more. When you take your weighing balance and you want to read the mass inside of this container and the mass inside of that container, obvious. This one, because it is more, we have more matter in this compared to there. So that means here, meaning the mass will be high. So mass, it is the property. But what type of a property? We say it is the extensive property, Why? Because whatever that you see here inside of these two containers over here, when you put your weight imbalance, it's going to be different because here we have a larger amount of this substance. Therefore, the mass will be high. You see, the mass depends on which one is large. The one that looks larger, it will have the greater mass. You understand? Even the volume, look at the volume. What's the volume over here? For an example, take a small container, take a big container. So here, the volume is less. Here, the volume is high, right? Meaning this, the volume, it is the intensive property because it depends on how many mass do we have this side and that side. I hope you understand what I'm saying. So looking at other examples of the intensive properties, we have the internal energy, we have the heat capacity, enthalpy, entropy, Helmholtz energy, and then we have the Gibbs we have the Gibbs energy. So these are their extensive properties. So tomorrow when I come to you and I say, or I talk about the internal energy, you have to understand what type of property am I talking about. Talk about the enthalpy, talk about the entropy, talk about the Gibbs energy. You're supposed to understand what type of property are we talking about, the volume. We talk about the pressure, we talk about the temperature, and all of those. So probably we'll learn more through the whole entire module. Now, while we are busy explaining the major definitions, we're going to look at the mixtures, right? In thermodynamics, right, we have what you call the homogeneous system. So when we talk about the homogeneous system, it's very important to understand this. That's why I want to read it so that you can understand it, okay? Look at this definition over here. Remember, we have already discussed what are the intensive properties, right? We are talking about the temperature, we are talking about the pressure, and so forth. So when you talk, homo means the same, right? So when you talk about the intense homogeneous mixture, we say it is the intensive properties change continuously and uniformly, meaning this is smooth. We're talking about a smoothly system, the system that is smooth. Okay, so meaning look at the temperature. When the temperature changes and it changes continuously and uniformly, when we say uniformly, it changes smoothly. It doesn't change like drastically just like that. You understand? So that type of a system that we'll be talking about, it will be called the homogeneous system. You understand what I'm saying? So if there is a continuous change and the uniform change of the temperature or of the pressure, that means we are talking about the homogeneous mixture. So looking at the substance that has a uniform thermodynamic property throughout is said to be homogeneous all the times, okay? And therefore, heterogeneous system, we are talking about the system made up of two. Hetero means different, by the way, hence why here we are looking at the keyword two or more. So meaning heterogeneous system, it is a system made up of two or more phases, right? In which the intensive property changes abruptly at phase contact surfaces. When you have, okay, let's have a look at this diagram over here. We have the purple, we have the green, right? The purple, they are more clustered together. They don't look like they mixed up together. The purple and the green, they look more separated inside of the mixture. So we can see that the purple clustered molecules and the green clustered molecules, they tell us that these substances, they are together, but they are separated from each other. You understand? So that means we are talking about the system that is heterogeneous. But here we have the purple that are mixed with green. These particles, they are mixed well together, so they do not indicate that they are more separated from each other. Therefore, here we're talking about the homogeneous system. I hope that makes sense. Now, another definition that we're going to look at the pure substances, right? Now, let's talk about the pure substance. Again, remember I said you should be able to distinguish between the pure substance and the mixture. And you need to understand that when you talk about the pure substances, we say the pure substances has the homogeneous, meaning the pure substance, it could be regarded as an element, number one, that's out. The pure substance could be regarded as a compound. And you have to understand, if a pure substance is regarded as a compound, it's regarded as a mixture of elements, right? When, for example, uh, sodium chloride, right? It's a compound which is combination of sodium and fluorine atoms. They combine together, right? You understand? So that's a compound. I'm just making an example of a compound, but you have to understand we have the pure compounds. So compound can also be regarded as a pure substance. And therefore, the mixtures can also be regarded as pure substance. So it's very important to understand that. So when you talk about the pure substance, it's where we have as homogeneous and invariable chemical composition and may exist in more than one phase. Now, the key word here is invariable chemical composition, meaning a pure mixture, the particles or the molecules of the pure mixture are perfectly mixed well together. For example, think of a coffee. Coffee is a pure substance. Ne? A brass, it's a pure substance because the molecules, they are mixed up together in a form that they are perfectly mixed. Correct? It's like a perfect match. You understand? So that's what we mean by a pure substance in a nutshell, so that it makes sense to you. What does that actually mean? Okay. But if if two substances they combine, okay, I'll show you the examples of not pure mixture. I wanted to explain this. So when you talk about not pure mixture, for an example, you can mix up a liquid and a vapor, right? So if you mix up a liquid and a vapor, do we have the invariable composition in that substance? No, we don't have invariable composition because we can tell that the vapor, it is separated from the liquid. So they are not perfectly fit. It's not like a puzzle. So I mean, when you talk about it, okay, the simplest analogy to understand what does the pure substance mean is when we talk about the puzzle. When the puzzle fit together, we are talking about the pure substance. But when the puzzle doesn't fit together, we are talking about substance that is not pure. Okay, I hope that makes sense. Even though the puzzles are not the same, but if they perfectly um, fit together, therefore we are talking about the pure substance. Okay, so now here, the composition of the liquid phase is different from that of a vapor. That's why we say the composition is the same. That's why I say to you, when I go back to this slide over here, the invariable chemical composition, right? Meaning, we have the chemical composition that are not different. They perfectly meet each other halfway. Okay, so now I want us to look at examples of pure substances, right? So the first example, we're talking about water. Water is a pure substance. We're talking about the solid water, we're talking about the liquid water, and we're talking about the vapor phases of water. We're still looking at the pure substance. And then mixture of liquid water and water vapor. Understand this. The mixture of liquid water and water vapor. We are looking at the pure substances, and then we have the carbon dioxide denoted by CO2. It's also an example of a pure substance. We're looking at the nitrogen gas, which is N2. And then the last example, we are looking at the mixtures of gases, right? When gases mix up together, you won't be able to tell which one is which. such as air. We know air has oxygen, nitrogen, right? But we have to understand that other gases that are mixed up into air. Yeah, so as long as there is no change of phase, as long as there is no change, there's no change of phase, therefore we have the pure substance. Okay. Why? So as much as we spoke about the pure substance, so basically from here, we're actually discussing more of pure substances. And then here we're talking about the homogeneous mixture, and then we spoke about the properties, the phase and interface, and the starting definitions of thermodynamics. So now what I want us to look at is the phase of pure substances. We're still under the pure substances, by the way. So when you talk about the phase of pure substances, I said to you, there are three of them. We have the solid, we have the liquids, and then we have the gases. So it's very important to understand how does these molecules arranged in a solid state. We can see that the molecules are tightly packed to one another, and the motion or the movement of these molecules, it's all about the oscillations, or it's all about the vibrations. They cannot move because they are close to one another, right? Why? Because they are tightly packed. And then when we look at the liquids, we can see that the molecules are not that tightly packed to one another, but they are close to one another, and they move relative to the motion. They move relative to the motion of the container. Meaning, is if this container moves, therefore these molecules will also move. So these ones, they do not move; they vibrate. That's how they move, these molecules. But this one, they take the shape. They take the motion of the container. Newton's first law of motion, right? And therefore, here we have the gaseous molecules, where the phase is called the gases. The molecules are far apart from each other, where the intermolecular force is absolutely weak. If this was an ideal gas, we would say intermolecular force is negligible, right? But because this is just the gas, which is not ideal, which is the real gas, we'll assume that the intermolecular force is very, very weak. Hence why these molecules are far apart from one another. So these molecules, they randomly move because they are in a gaseous state. So these are just the phases of pure substances. So now here, we'll look at the phase changes processes, where we're going to look at the pure substances. Let's catch this session on the next video.